someone might have the same question or similar. Of course, I don't share your name, but someone emailed me yesterday, and they were referring to this document that the most recent one I put on D2L, and the after having the prerequisite material under control, the second thing, the introductory material always being prepared for class, and their question was really about the two quizzes that are coming up. And so let's talk about that for a minute. So this is the week of the 12th in the lab. So you do have two quizzes. One is called the Intro to A&P quiz. And that's 50 points. And so what they were really after was, specifically what sort of things do I need to be focusing on? And as always, the bottom line, the lecture notes, okay? But specifically, pages 1 through 7 of the lecture notes. In the textbook, chapter 1. I think omit homeostasis for now. Omit the 4 quads and the 9 regions. And those are these two pictures that I may have pointed out on Monday. So these 4 quadrants. These 9 regions, and depending on which book you have, these are on page 16. So that's the most current book. If you've got the orange book or something else, I don't know what page they're on. Right in the lab manual, it's exercises 1 and 2. But again, omit the 4 quadrants and the 9 regions, and omit the rat dissection, which is obvious after going to lab this week, because you said, well, I didn't even see a rat, much less dissect one. And then in the atlas, pages 1 through 5. So that's the Intro to A&P quiz, sort of as definitive as I can be. But again, your bottom line is always the lecture notes. And then, well, what did we talk about in this room on the lecture notes, and what parts of these resources go with the lecture notes. All right, the solutions quiz is the same day. Again, 50 points. Lecture notes, page 8. Chapter 3 in the textbook. A lot of chapter 3 is review material, cell structure and function, DNA replication, protein synthesis. But the parts of, and of course, all of that is going to be on exam 1, but as far as the solution quiz goes, the parts of chapter 3 that I would say are just good resources for you, where it talks about diffusion, osmosis, and tonicity. Then a good source to read is exercise 5 in the lab manual. We don't do anything with exercise 5 in the lab. There are no review questions referenced in the syllabus for exercise 5. But if you threw away your Biology 111 books and you really need a good review of osmosis and all of that, this is a good source to read. On the prerequisite document, page 8 sort of gives you an outline of all of this. We'll leave it at that. So this is as definitive as I can make it. We just got started with molarity because we saw that percent, while we can compare like solutions or solutions of the same solute, percent doesn't allow us to compare solutions that are composed of two different solutes any more than we can compare rupees to yen. We need that common denominator, which is not molarity, but molarity is getting us closer to the common denominator. We'll continue with our little on the left stuff you're transferring to an index card, the meat of it, the stuff I absolutely cannot let escape me. So we've got molarity, mole solute over a liter of solution. And we saw that the simplest problems in molarity are mathless math, just like they are with percent. If we've got 2 moles of glucose in 500 mils, that's a 4 molar solution. Moles per liter, so if we have 2 moles in 500 mils, we have 4 moles in 1,000 mils, and 1,000 mils is a liter, so we have 4 moles in a liter, which is 4 molar. So we went through 4 or so of those mathless math problems. What's next is to talk about how we deal with molarity or moles, and then molarity when we're given grams. So we need to be able to convert back and forth between grams and moles. And if you like formulas, it would go like this. The number of moles equals the number of grams divided by the molecular weight. Or the number of grams equals the number of moles times the molecular weight. I personally don't like formulas. I like to make sense out of things. I like to understand things. But sometimes when you're learning, I realize, I appreciate that a formula might be necessary. But let's see if we could make sense out of this in such a way that we negate the need for a formula. In other words, nobody in the room has committed to memory that the number of feet equals the number of inches divided by 12. If I tell you Billy's 76 inches tall, you can just tell me what his height is in feet. You don't need a calculator, you don't need a formula. But if you were from another country and had never heard of feet and inches, you might need a formula until you got comfortable with the way we do things. Yeah.
Just real quick, in your notes, you've actually got the complete backwards of those formulas.
Then the notes are wrong.
Okay.
Let's make sense out of it and see. So yeah, until you got comfortable with this, you might tell me that Tom, who is 72 inches tall, is 864 feet tall. Now, none of you would do that because you probably all grew up with feet and inches. But if you'd never heard of feet and inches and just came to the United States, you might do this. And you might not even catch it as a ridiculous answer. Who could be 864 feet tall? Clearly what the person did is they multiplied 72 times 12 instead of 72 divided by 12. Well, see, we make those same mistakes when we deal with the metric system. Because we didn't grow up with it. Your children are growing up with it, and some of you perhaps grew up with it. Children today learn both systems simultaneously. But if we don't use a formula, we're not so likely to make a mistake. And man, that's, oh, here's the attendance. What page? Is that page 8?
I stretched out my pages, so I don't
Okay.
have different page numbers.
Page 8, letter F. Let's everybody fix this. Page 8, letter F.
I think it's correct.
No, it's correct.
You got moles up there is grams divided by molecular weight, but you've got grams times molecular weight.
That's
Right.
what it just said.
Number 1 says to go to moles to grams, you'd multiply grams by the molecular weight.
The board's different.
Yeah, the board is different. Because you've got,
Okay, yeah, this is wrong.
okay.
This is wrong. So number 1 should say to go from moles to grams, you want to divide by molecular weight. Number 2, to go from grams to moles, you want to multiply by molecular weight. So guys, I made a mistake. Any of you that are perfect, feel free to stand up and throw whatever you want at me. I will remain motionless while you do it. Go ahead. But you must be perfect in order to be allowed to do that. Thank you for catching that. So again, let's see if we can make sense out of this. Is there something that we know the molecular weight of? It's on your list over there on the right. It's on your index card now. Glucose. Glucose. What's the molecular weight of glucose?
180.
And that means 180 grams per mole. So if I have 180 grams, how many moles do I have? 1. What if I had 360 grams?
2.
How many moles? 2 moles? Okay. What if I had 720 grams? How many moles would I have? 4. What if I had 90 grams? 0.5. 0.5. Now, for the most part, most of you were able to manipulate these numbers because they correspond to a circle. So you grew up manipulating those numbers. It might be because you were in Girl Scouts or Boy Scouts. It might be because you're into GPS and geocaching. It might be because you're into snowboarding or skiing, and the half pipe and 720 is what. And for whatever reason, most humans manipulate these numbers effortlessly. I don't care why or how you were able to manipulate them. You were. But what is the math if you were from another world and you had to figure this out? You've got 360 grams of glucose, and that works out to 2 moles. What is the math there?
Double the original amount.
Okay, you don't have the original amount. So now what's the math? It's mathless math, I know. But if you had to figure it out, if you had to teach it to somebody, what'd you do right here?
Number of moles times.
You said 360 divided by 180 equals 2. What's the 360? It's the number of grams you have, right? What's the 180? The molecular weight. And what's the 2? Number of moles equals number of grams divided by molecular weight. So instead of memorizing this, could you make sense out of it like that? If you memorize this and you forget it, and you're taking a test, could you ask yourself, what did I do here mathematically? Okay, some of you hate math, and that's okay, but I urge you to employ this method, because when you start memorizing formulas, you make huge mistakes. So we'll put that over here. Number of moles is equal to number of grams divided by the molecular weight. And if we need that, we'll use it. So now, calculate the number of moles in 54 and a half? It's on your card. Someone look, please. 58 and a half. Okay, I knew something wasn't sitting well. Calculate the number of moles in 58 and a half grams of sodium chloride. 1. Why is it 1? Because the molecular weight of sodium chloride is 58 and a half. And that's on the far right. It's on your index card from Monday. The math there was number of moles is equal to the number of grams divided by the molecular weight. 58 and a half, that's how many grams you have, divided by the molecular weight, 58 and a half equals 1. Calculate the number of moles in 2,346.81 grams of calcium bromide. It's no longer mathless math. What's the first thing we need? Molecular weight of what? Okay. So we go to the periodic table. We use all of the decimal places. So 79.904. I've got 2 of those. 40.078. Got 3 decimal places with each one, so I will use all of them. So my molecular weight 199.886. So 2,346.81 divided by 199.886, whatever that equals. One 1.741 moles. I'll round it now to to 2 decimal places, which is typically what I want you to do. Occasionally the instructions will tell you how many decimal places to round to. If they don't, round to 2. If it's multiple choice, round the way I round it, okay? A, B, C, D, E, well, however I round it is the way you need to round it. Applying this to molarity is no big deal. As always, the questions start with mathless math. Calculate the molarity of a solution containing 90 grams of fructose in 1 liter. What do we want? We did it this way on Monday. We want molarity, which is moles per liter. Anyone have the answer yet? I assume you all have it. You just don't want to look like smart alecks and scream it out. What was I given? 90 grams in 1 liter. What's the math to go from grams to moles? Anyone? Tell us. Divide by molecular weight. So 90 divided by, what's the molecular weight? 180 over 1 liter. So what do I have now? 0.5 over 1 liter. So what's the molarity? 0.5 molar. Calculate the number of moles in 360 grams of galactose. The answer is? Calculate the molarity of a solution containing 360 grams galactose in 1 liter. It's the same thing, isn't it? 2 molar. Calculate the molarity of a solution containing 720 grams of fructose. Okay, how many moles is that? 4. So as you read it, 4. Now that's cemented right there in the frontal lobe. 720 grams of fructose in 10 liters. So you've got how many moles? 4 moles. And how much? 10 liters. So how many moles do you have in 1 liter? 0.4. So what's the molarity? 0.4. Three hundred 62.81 grams of potassium chloride in 2 liters. What is the first thing I need that's not written down there for me? Molecular weight. So to the periodic table we go. 35.453. Potassium, 39.0983. I'll use 3 decimal places because while I have 4 for potassium, I only have 3 for bromine. What do I do with the molecular weight and this number? Divide? Molecular weight divided by this? Opposite, okay. So 362.81 divided by 74.551. Now I have moles. I still have that over 2 liters. So I do the division. And I get 4.867 moles over 2 liters. What else do I need to do? Divide by 2. Why am I dividing by 2? I've got to change this to 1. When I divide this by 2, I have to divide that by 2. So I've got 2.433 moles per liter. So what's the molarity? 2.433 m. 2 decimal places. Molarity's a little better than percent. Still not very good. Because if I want to know about 4 molar sodium chloride versus 4 molar magnesium chloride, I know that the 4 molar sodium chloride is less than the 4 molar magnesium chloride. But the way I know that, the reason I know that, and this, by the way, is where we stop Biology 111, and now we're getting into something new. Some of your Biology 111 teachers cover Oz, some don't. So I just assume that they don't. So this becomes 8 Oz molar. This becomes 12 Oz molar. That I assume I need to explain. Again, some of your Biology 111 teachers cover Oz, some do not. So I just assume that I need to cover this. So what is Oz? Well, Oz does 2 things, one of which I did right here. It accounts for all ions in an ionic compound. So my sodium chloride, when put in water, becomes an ion of sodium and an ion of chloride. So this is 2 ions. Magnesium chloride, on the other hand, breaks apart into 3 ions. And we can see that right here. There's 1 sodium and 1 chloride. There's 1 magnesium and 2 chlorides. So this becomes 3 ions. So when we're dealing with tonicity, which becomes extremely important in renal physiology, how the kidneys are behaving, what hormones are we producing or not producing to cause us to retain or eliminate water, what hormones are we producing or not producing to cause us to retain or eliminate sodium. And of course, are sodium and water related? Yes, because of osmosis. So if we retain sodium, we retain water. So this is not just for fun, this is huge physiologically. So for my sodium, I said I've got a molarity of 4 times 2 ions. 4 times 2 is 8 osmolar. For my magnesium chloride, I said I've got a molarity of 4 times 3 ions. 4 times 3 is 12 osmolar. So that's one of the 2 things Oz does. What else does Oz do? Accounts for all solutes in solutions containing multiple solutes. So let's say I have a solution, call it solution A, and it is 2 molar sodium chloride and 3 molar calcium bromide and 1 molar potassium bromide. And I need to know the concentration of the solution. Can I say 2 plus 3 plus 1? No. Just like I can't say 1/2 plus 1/3. I need my common denominator. So what's the osmolarity of the 2 molar sodium chloride? 4. Big O, small s, big M. The calcium bromide, how many ions are there? So what's the osmolarity? 9. 3 molar times 3 ions. 1 molar potassium bromide, that's 1 times, how many ions do you see there? So that's 2 osmolar. So 9 plus 2 is 11, plus 4, so 15 osmoles is the concentration of the solution. So Oz lets me do 2 things. It lets me account for the ions in my ionic compounds, and it lets me add the concentrations of individual solutes together. Do you think there are more than one solute in our blood?
Yes.
Oh, yeah.
Say there's thousands. So how are we going to calculate the concentration of solute in our blood? Well, we've got to know the osmolarity of everything in there. We don't have to do that. It's been done for us. But that's what had to be done. Let's do another one of these, because I've made a point of using salts or ionic compounds in my examples. And things are a little different when we have covalent molecules. Calculate the osmolarity of the following solution. And let's put Oz on this list of stuff that gets transferred to your index card. So this solution is 2 molar sodium chloride, 1 molar potassium bromide, 2 molar calcium chloride, 3 molar magnesium bromide, 2 molar glucose, 3 molar sucrose. So before we can add the numbers together, we have to do what we just did. We have to convert each solute from molarity to osmolarity. Sodium chloride, it's a salt, ide. It's ionic. How many ions are in there? 2 ions times the molarity of 2 gives me 4 osmolarity. Potassium bromide, ide, it's a salt. It's ionic. 1 molar times how many ions? So 2 osmolar. Calcium chloride, ide, it's a salt. It's ionic. I see 3 ions there times a molarity of 2. 3 times 2 is 6 osmolar. Magnesium bromide, ide, it's a salt. It's ionic. 3 ions times the molarity of 3. 3 times 3 is 9. What do my salts have in common?
They're all ionic.
They're all ionic, okay? And they're ionic, they're salts, they end in ide. And what do we have going on over here when we have ionic compounds? Takes us back to the early parts of the prerequisite document. We have the red stairs. Everything to the left of the stairs is a metal. The metals lose electrons and become positive. We call them cations. The nonmetals gain electrons and become negative. We call them anions. The cation and the anion, being oppositely charged, they're attracted to each other. We call that an ionic bond. That is why when we mix them in water, they break apart into the respective ions. That is why it's very, very easy to dissolve salt in water. What are these molecules that end in ose? Are they salts? No. What are they? They're sugars. And what type of bond do we have between the atoms and sugars? Covalent. Covalent. So if we take glucose and we put it in water, nothing happens to the bonds between the atoms because they're covalent bonds. They're not ionic bonds. So this is one particle. 1 times a molarity of 2 gives us 2 osmolarity. Sucrose. Sucrose is glucose plus fructose. In other words, 2 monosaccharides combine to form table sugar. What happens when we put sucrose in water? In other words, what type of bond is between glucose and fructose? A covalent bond. This doesn't break apart when we put it in water. When you put sucrose in water or iced tea, it doesn't do anything. The glycosidic bond between the glucose and the fructose does not break when you put it in water because it's a covalent bond. It's not an ionic bond. So even though this is a disaccharide, it's one particle. One particle times a molarity of 3 gives us an osmolarity of 3. So when you're converting, let's see, this is sugar. The sugars are covalent. So when you're converting from molarity to osmolarity, if it's a salt, you need the Oz factor. And the Oz factor is how many ions are there. If it's a sugar and you're converting from molarity to osmolarity, the Oz factor is always what? 1. 1 times whatever is whatever. So the 2 was multiplied by 1, the 3 was multiplied by 1. It's not that there's not an Oz factor, it's just that the Oz factor is 1. Basically, you have your ides and your oses. This is an excellent example of where chemistry in biology and in physiology is so simple because we don't work with all of the things that chemists work with. When you look at this periodic table, there's maybe 4, 5, 6 things over here we're ever going to use in our life. There's another 5 or 6 over here, maybe 8 we're ever going to use in our life. We don't care about all the other crap. You take Chemistry 111, it becomes extremely important. Extremely important. Then Chemistry 112, Chemistry 211, Chemistry 2. Yeah, oh man, it becomes a nightmare. But we're stupid when it comes to chemistry because the only chemistry we need is the chemistry for physiology. All the chemistry in the world was written on this board. Here's what we have to know as physiologists, or as nurses, or as brain surgeons. That's all we have to know out of everything written on the board. So it makes it extremely simple for us. It's an ide or it's an ose. It's a salt or it's a sugar. I ask you again, do you think that there are a lot of solutes in human blood? Yeah, of course there are. And in addition to the salts and the sugars, when the people that did this for human blood did it, in addition to the salts and the sugars, they had to consider the proteins. They had to consider the hormones. Some hormones are proteins. Some hormones are steroids. They had to consider both. They had to consider the gases, the oxygen and the carbon dioxide. They had to consider the gases that are present in minuscule amounts. We have helium in our blood. Nobody's ever going to talk about it, but it's there. We have gold in our blood. They had to consider that. Okay, they had to consider everything. And when they took the molarity of all of these things and converted it to osmolarity, as we just did, but when they did it, they had thousands of things so they took the molarity of sodium chloride, the molarity of glycogen, estrogen, testosterone, angiotensin, prothrombin, oxygen, carbon dioxide, everything. They converted them all to osmolarity. When they added them all up, the answer was 0.290 osmoles. That is the concentration of our blood. So even with everything in there, it's still a tiny, tiny, tiny number. Now you guys know all about the metric system. Now it's all based on 10 and therefore effortless and easy. You probably wouldn't tell me that you lived $1,746,141,732.28 micrometers from the college. You'd probably convert that to kilometers, or maybe even miles, because we're in America. So we tend to put things in units that make sense. So with that in mind, the way we refer to this is 290 milliosmolarity. Okay, so we can milli whatever we want to milli. If someone is throwing a ball and you measure how long it takes the ball to go from here to there, and you say it took 0.0048 seconds, we would call it 4.8 milliseconds, because we're just more comfortable with 4.8, or maybe we're not, but most people are, than 0.0048. So we multiply this times 1,000 and prefix it with milli. So at the top of your list over here, if you have your little index card with you, just get it out and modify what's at the top. But somewhere up toward the top, it may not be the tip top, I don't know. You have isotonic solutions as 0.85% sodium chloride, and when I wrote that on the board, I said your biology teacher might have called it 0.9% sodium chloride. You also have 5% glucose, which is also referred to as 5% dextrose. What you want to add to that part of your little note card is 0.290 osmolarity, or 290 milliosmolarity. So when we talk about a cell in fluid and is the net movement of water in or out, or maybe there is no net movement. And in the clinical world, we want no net movement. And to accomplish that, to achieve that, we need to use isotonic solutions. So these are the solutions that we infuse into people. When we have this discussion, what's going on is the cells are 290 milliosmoles. The fluid needs to be 290 milliosmoles to be isotonic. Well, so we need a salt solution and a sugar solution that are isotonic to our blood plasma. So we had to, yeah.
Sorry, I'm probably breaking things too early, but what would happen if somebody, let's say, this actually happened to a friend of mine, drank too much water and the electrolytes and salt count in her blood plummeted, and what would this?
Then they
solution
have
be
what is
different?
called hyponatremia, hyponatremia, low sodium. Then they would be administered a hypertonic solution in the emergency room or wherever they were.
How would they determine exactly how much to give her?
By, well, first of all, you determining that draw blood, run it through the lab, see what the sodium concentration, see what the milliosmolarity is, and then start administering a hypertonic solution and repeat the labs, whatever the doctor thought, every 10 minutes, every 30 minutes, every hour, depending on how severe it was. This happens a lot in Colorado because the air is so dry. We used to misdiagnose it all the time as altitude sickness because it happens to our tourists who come out here to compete. I don't know how familiar you guys are with the crazy things that go on here, but we have what we call simple races, like the Collegiate Peaks 50-mile trail run or the Lake City 50-mile trail run. Moderately difficult races like the Leadville 100-mile trail run. We have the Hard Rock 100-mile trail run, which is one of the most ungodly things on earth, I suppose, except that it's only 100 miles. So when people from Missouri come here and they get sick, we go, it's altitude sickness, it's got to be altitude sickness. And they're treated with ordinary saline and oxygen, and they just get worse. And somebody finally realized that, man, these people are hyponatremic. They need a concentrated solid solution to get beyond this. So we realized the need for a salt solution and a sugar solution, both of which are isotonic to our plasma. We wanted simple solutions. We didn't want solutions that had, 487 solutes that cost a lot to mix. So we ask, what percentage sodium chloride and what percentage glucose approximately equals 290. Didn't have to equal it exactly, hence my approximate sign there. We knew that there was a clinical range of about 270 310. So we wanted these solutions to, well, they had to fall within this clinical range, but we wanted them to be easy to mix, easy to measure. Didn't want some, crazy thing like 4.723% or 5.018% or 0.846. We wanted nice round numbers. And because there's a clinical range, we could come up with nice round numbers. And the numbers they come out to 0.85 and 5.0. Your cells nor your plasma, none of it, none of you, nothing about you is 0.85% salt. Nor are you 5% glucose. We use these numbers because they equal 290. You are nowhere near 0.85% salt or 5% glucose. But because when we make NIV, we don't want to have to put minuscule amounts of 387,000 things in it. We use something that equals the 290. So we can administer calcium chloride solutions, anything, as long as it falls in that clinical range. So let's calculate the milliosmolarity of these things. Now, when you're faced with these types of problems, the first thing to do is calculate the molarity. We've done a bunch of those. Grams divided by molecular weight gives you moles. That's simple. Once you have the molarity, account for Oz. What's the Oz factor going to be when we do this for glucose? 1. What's the Oz factor going to be when we do it for sodium chloride?
2.
So basically all we're doing is calculating the molarity and then either multiplying it by 1 or 2. There's no math there. And then what do we do for milli? Multiply it by 1,000. Remember guys, you can milli anything. So the meat of the problem here is molarity. And molarity is simple. It's grams divided by molecular weight. That's all there is to it. So this is super, super simple. So we have, and you might, again, when you're in these learning phases, what do I want? What was I given? So that I understand, what am I trying to do here? Well, I'm given here 5% glucose. What's percent? Goes back to Monday. Grams over 100. Can't do anything with this. We have to expand the units. So we have 5 grams